This lesson focuses on operations on radical expressions, with a particular focus on dividing. So here are a bunch of examples we're going to go through. You can pause it, try them on your own. But the key thing here is that we want to rationalize the denominator. So the goal is to never have a root in the denominator. That's what rationalizing the denominator implies. It's a format issue, but you never want to answer with a root in the denominator. So let's talk about how to get rid of the roots from the denominator if they are there. So in the first example, you have root 2 in the denominator. Now it's a fraction, so we're allowed to multiply the numerator and the denominator by the same thing so that the fraction is still the same. So in this case, what would you multiply root 2 by in order for the root to disappear? Now, one key thing that people likely are to ask is, why can't we just square the numerator and the denominator? Well, what if you had 2/3? Is that the same as 4/9? No, it's not. So you can't just square the numerator and the denominator like that. The only thing we're allowed to do to a fraction is multiply or divide the numerator and denominator by the same number. So in this case, we've got root 2. If you multiply it by root 2, then you will have root 4, which is 2. You could also see it as the fact that it's 2 squared, and it's a square root. So if we do that to the denominator, we also need it in the numerator. So this set of examples is all to do with a monomial term. In the next set, we'll look at what happens when you have binomials in the denominator. So here we're left with 2 root 2 over 2, which in fact simplifies to being a root 2. It's a little simpler than 2 over root 2. Alright, let's take a look at the next example. What would you multiply the numerator and denominator by so that the root 3 is gone? We want no roots in the denominator. Well, in this case, just multiply by root 3. You don't have to multiply by the exact same thing that the denominator has, just by whatever is missing from the denominator to simplify the root. So here we'll have 3 root 15 over 2 times, and this is 3 squared. So that's 2 times 3. Now you'll notice you could say 3 root 15 over 6, or you could see that these are common factors because of the time sign. Make sure you don't cancel if there's a plus. So that's root 15 over 2. Now in this example, you can see that the square root will be in the numerator and in the denominator. So our denominator needs some bits in order for it to be able to simplify completely. So what's missing? What do we multiply by? Well, if we multiply by a 5, then the 5 will be 5 squared, and that'll cancel. If we multiply by another x, that'll be good. And y squared already simplifies, so that's fine then. So we just need root 5x to multiply. So that's negative root 15x over, and now the 5 squared in a root becomes a 5, x squared becomes an x, and y squared becomes a y, and you're done. In this case, we've got a cube root, so you've got cube root 5 over cube root 2x squared, and now we want to multiply numerator and denominator by something so that the denominator will not have a root. We don't care if there's anything left for roots in the numerator, but the denominator cannot have a root. So, what would you put in? Well, 2 times 2 will give us 4. Cube root of 4 doesn't simplify. You can see 4 though as 2 times 2. Hey, we need triplets here. So we actually need to multiply by 4, which is 2 squared, in order for the cube to simplify. And then we're also missing an x in order for this to be x cubed. So now we do that to the numerator and the denominator. And in the numerator, because they're both cube roots, we can combine them. 5 times 4 is 20 and x. And in the denominator, this is actually, I'll write this out, we've got cube root of 2 cubed times x cubed. So that is same numerator over 2x. Now try this one. This is a 4th root, meaning we need to multiply by a 4th root. So don't forget that little 4 there. And we need groups of 4. So here we have 2 x's, and here we have 3 y's. So we need 2 more x's in order for this to be x to the 4 when multiplied. And we need 1 more y to make this 4 y's. So we do the same thing to the numerator, and we have x 4th root of x squared y over, it'll be 4th root of x to the 4, y to the 4, which is what we wanted so that the root disappears. And so we've got x 4th root of x squared y over xy. And the x's cancel because it's a common factor. And so we're just left with the 4th root of x squared y over y. And the last one, see if you can figure out what you would multiply this one by. So you have 1a, so you need 4 more a's to make 5. You have 4 b's, and you need 1 more. And you do the same thing to the numerator. So this one's got negative 5th root a to the 4b over, and then this was a to the 5, which simplifies to just a, and b to the 5, which simplifies to just b. Now, what if there are 2 terms in the denominator? So we can't just go ahead and multiply by root 2, because that'll actually make it root 2 minus 2, and we still have a root. You can try that out. Doesn't work. So the goal is, what do we take 1 minus root 2 and multiply it by so that no roots are left? Well, there's this fun fact here that we've seen over and over again, and this is the difference of squares. And you should by now notice that if you expand this, the middle terms cancel, and the middle terms are the ones that would have had the roots. So this is actually a great formula to use to rationalize the denominator when you have a binomial in the denominator, because you end up with both terms being squared, and therefore if it was a square root and you squared it, it wouldn't be a square root anymore. So we've got 1 minus root 2, and these are called conjugates to each other. These 2 brackets are called conjugates. So you might see or hear someone say multiply by the conjugate. So the other part of the difference of squares formula would be the 1 plus root 2 version. So that's what we want to do to the numerator and the denominator. And therefore in the numerator we have to expand, so we have root 2 times 1 plus root 2 times root 2, which is 2, over the difference of squares. You can expand this, but you'll know that it's the first term squared, which is 1, minus the last term squared, which is 2. And so that actually simplifies quite nicely. That becomes root 2 plus 2 over negative 1. You could actually split it, root 2 over negative 1 plus 2 over negative 1, giving you negative root 2 minus 2. It's a little simpler. Here we have roots in the denominator again. I don't care if the numerators are there, but the denominator is the big part. So what is the conjugate to this that will multiply it and cause it to not have any roots anymore? So the bottom is a plus, so we want to multiply by the minus version so that the bottom becomes all squared. Now the numerator, I don't really care, it just has to be the same as what I did to the denominator. So when you expand this, you will notice that because this is root x minus root y times root x minus root y, it's actually root x minus root y squared. So you can multiply it out, FOIL it out, but you will notice the middle term doubles. And the middle term comes from the middle term. So that's root x squared from the first times first is x minus twice the middle term, which is root xy, and then plus root y squared, which becomes y. So be careful with writing those out very carefully. And the denominator is the first term squared, first times first, minus the last term squared, last times last. The middle term in this case, because the signs are different, will not double, but it will cancel. So don't use these formulas unless you understand how they are created, because you don't want to cause yourself to memorize random rules and use them in inappropriate places. Okay, so that's about it. I know this may be calling you to cancel here, but the x's and y's, they're not factors. So if there's a plus or minus, you can't cancel. Only if there's a times sign you can cancel, in the sense of crossing out. And the crossing out is essentially a division. So we can't divide both top and bottom by x or by y. So be careful there. This is about all that you can do with this. So you just leave it. Alright, we got our little reminder here again. Same thing, we've got a binomial, so then multiply by the conjugate, which is root a plus 4. So try this out on your own and see if it works out for you as well. Now this one we do need to distribute completely because it's not a special format. So first times first gives you a root a, and then you have plus 4a minus 16 root a and minus 16 times 4, which is 64, over, and now this conjugate will be a squared, root a squared, which is a, minus 4 squared, which is 16. And there are some, no common terms in the numerator. I thought the root a's were, but this is an a. So we can't do anything further with this, so we just leave it. And this last one here, we've got conjugate is going to be 3 root 5 minus 2 root 3. And do that to the numerator and see how that goes for you. Multiply these out by 2, you get 6 root 5 minus 4 root 3 over, and then now we're squaring the first term minus the last term, or you can multiply everything out completely. So that'll mean we're squaring the 3, which is 9, times squaring the root 5, which is just a 5, minus squaring the 2, which is a 4, times squaring the root 3, which is just a 3. So be careful with them having roots or not roots. So the numerator we can't do anything with because they are different terms, not like terms. But the denominator, we have 9 times 5, so 45 minus 12, 33. Now this is all you can do with this. If you really like, you could separate it So you could write it as 6 root 5 over 33 minus 4 root 3 over 33 and see if there's anything that simplifies. In this case, 6 over 33 both divide by, notice that canceling means divide by. They divide by 3, giving 2 and 11. So you could write 2 root 5 over 11 minus 4 root 3 over 33. These are both correct, so yeah. It's always good to check if something simplifies. Sometimes something nicer simplifies. You could also look at factoring out a common factor and seeing if it simplifies. But in this case, that's really all we can do. So here's a couple more that have to do with simplifying it once the root is gone from the denominator. So notice these don't have roots in the denominator, but maybe this is what happened after you did the rationalization. So this is exactly what I'm talking about. So you could actually split this up into two fractions, or you could factor the numerator and that's probably a nice clean way to do it. So in the numerator there's a common factor of 2, right, because these both terms divide by 2. The root 2 is kind of like your x, so that's 1 minus 3 root 2. If you multiply it back, you should get that again, over 4, and because this is a times, you can now simplify. Notice you cannot simplify this 2 and 4. There's the minus, they're not factors to be simplified. So 2 over 4 is 1 over 2, and so that simplifies to 1 minus 3 root 2 over 2. So that's just a simpler way of expressing that. And same here. Now in this case, the root, you can actually simplify it because root 400 is 20. So let's just simplify that first. So that's 20, and then there's an x squared that comes out because x cubed is 2 and 1. So the x squared comes out as an x, and there's an x left inside, root x, over 5x. So let's factor the numerator. So a 10x can come out, and we've got 1 plus 2 root x over 5x. And now there's a common factor here, 1 and 2, and x are also common factors, leaving you with a nice simple form of 2 times 1 plus 2 root x, which you can leave like that, or 2 plus 4 root x. Both acceptable answers.